Okay, here I'm going to continue the discussion of multimode fibers, and I just showed a video of the Infinicore fiber and talked about the OM1 spec, showed the spec sheet under the camera here, and now I'll talk about the clear curve multimode. If you want the enhanced performance of the OM2, OM3, or OM4 varieties of multimode fiber, you're going to have to go to clear curve multimode. And in addition to offering the higher bandwidth distance products of OM2, 3, and 4 specs, ClearCurve also is their more modern type of multimode fiber that offers much better bend performance. And this is due to what's called the ClearCurve technology. It's proprietary to Corning. It offers enhanced bend performance. Typically, bend performance is specified only on a very loose spec. So typical bend performance specification is something like a small loss on a mandrel wrap of 30 to 100 millimeters. So a mandrel is just a cylinder. So what they do is they wrap the fiber around a cylinder, around a larger diameter cylinder, and sometimes they specify 1 wrap or 10 wraps or 100 wraps around sort of a large cylinder. Here, 30 to 100 millimeters. So it's pretty large, and so it's not a very small bend radius. Okay, so you can't bend the fiber in too tight of a circle. And small loss meaning a few tenths of a dB typically. However, in these multi-mode applications, in the data center or in an office building, for example, we've often got the fiber running through walls and through conduit and around corners, maybe even getting stepped on and pushed off to the side by somebody's foot on occasion. And bend performance is really very important, and you need to actually be able to go around corners. And so enhanced bend performance specs are given. And so we're typically given mandrel wrap diameters of 10 millimeters. So now we're wrapping the fiber around a 1 centimeter, something like this pen. That's a tight bend. And we're getting something like half a dB loss on that wrap. Okay, so what I'll do now is I'll just show you a couple of bend loss specs. First I'll show you sort of an SMF 28. This is a fairly common single mode fiber. And how do they specify the macro? Okay, this is called the macro bending loss. Yeah, enhanced typical bend performance spec. I should be calling this macro bend performance, macro bend loss, low macro bend loss. Okay, and so here's the macro bend loss spec on this fiber, and they say that the mandrel diameter is either 32, 50, or 60 millimeters. On the 32 millimeter diameter cylinder, 1 turn at 1550 gives less than a tenth of a dB attenuation. 50 turns on 100 millimeters at either 1310 or 1550 gives less than 0.05 dB of attenuation. That is induced attenuation, induced due to the wrapping, due to the bending. And at a 60 millimeter diameter, you can go 100 turns at 1625 with less than 0.05 dB of loss. It turns out that longer wavelengths have a larger mode, and therefore the mode reaches further out into the cladding, as we've seen in Chapter 4 and early here in Chapter 5 when we talk about confinement. And so longer wavelengths have less confinement in a given fiber, and the less confinement you have, the more bending loss you have. So longer wavelengths like 1625, which are sometimes used in fiber optic links for control signals, muxed in on top of the information signal, they often experience very high loss in optical fibers because of their poor confinement. In any case, so macro bend loss, large diameters, mandrels, 1 or 100 turns, very low loss. If we go to the Infinicore and look at their attenuation, they give the attenuation at 850 and 1300 as 2.9 dB per kilometer and 0.6 dB per kilometer at maximum, respectively. And then they just give a little sentence down here at the bottom that says induced attenuation from 100 turns around a 75 millimeter mandrel is less than half a dB at 850 and 1300. So again, it's a large mandrel here on the Infinicore multimode fibers. Okay, but now we go to the clear curves and look at the clear curve fiber spec. So here's the clear curve multimodes, and as I showed, this one has the OM4, OM2, 3, and 4 varieties. But this spec sheet shows you now the macro bend loss specs here as being on a 37.5 millimeter or a 15 millimeter or as small as a 7.5 millimeter mandrel. 7.5 millimeter mandrel means we're wrapping the fiber essentially around something about the size of my pen. That's a very sharp bend. At 37.5 we can take 100 turns and still have very low loss. Again, bending loss for longer wavelengths is always higher due to poorer confinement. And at the 15 or the 7.5 we can get away with 2 turns at less than 0.2 dB or less than 0.5 dB loss. This is an amazing spec for a bend performance of a fiber. How do they do it? Clear curve fibers use a proprietary technique, which is, as Corning describes it, a nanotechnology technique that during the manufacture of the fiber, basically what they do is they have the core and they have the cladding, and what happens is surrounding the core will be what is effectively a mirror type of structure. So here's the core, and this is a mirror type of structure, which provides an additional layer of confinement. Okay, so the problem with bending loss, and I think I have some slides on this from earlier. Let me show you that real quick. I may be running out of time, but in Chapter 4, when we talked about bending loss, I showed you the picture of the mode sort of going around the corner. Let me see if I can find that picture here real quick for you. Sorry for the delay. I thought I had it here. Okay, I don't. Showed the mode going around the corner, and the reason we have bending loss is that the mode tends to escape from the core out into the cladding. Well, this extra mirror structure tends to keep it confined within this radius, a couple of diameters of the fiber core. It's very small, right in there near the core, 10 or 20 or 30 microns out from the core, and it keeps the light inside this region. And when it's in this region, a certain amount of it's going to get coupled back into the core. And that's how it works. So you have light escaping due to bending. You have light escaping out into the cladding, but then it gets confined to a very narrow region of the cladding and stays in there. One thing I haven't mentioned yet is cladding modes, and it turns out that the fiber itself, if you go all the way to the surface of the cladding where it meets the air, that surface also can give you total internal reflection. And it's possible to get light bouncing around out in the entire cladding, and sometimes those are called cladding modes. In any case, the clear curve technology is some sort of a nanotechnology technique. They don't describe it because it's proprietary, that creates this mirror here and recaptures the mode. Into the core after it escapes. Okay, I'll quit here. Thank you.